Yellowstone National Park's geysers and hot springs are world famous, but they're just the tip of the geothermal iceberg. In fact, there are places around the world where geothermal energy is more than twice as powerful as it is at Yellowstone. What are these places? Why do they have so much geothermal energy? And could we use this energy to power our homes and even entire cities? This is my channel. Join me to explore the unexpected science behind Earth's hidden geothermal powerhouse. In today's episode, we are going beyond Yellowstone to discover why certain areas of Earth's surface are warmer than others. It's August 2025. You may know that Earth is powered by a dynamo deep inside its core. Moving, sloshing and swirling layers of liquid metal generate electric currents and magnetic fields. And these magnetic fields are really important because they protect life on Earth from the harmful radiation of space. But it's not just the movement of metals that's happening beneath Earth's surface. There's also convection in the mantle, the thick layer of rock between Earth's core and crust. Hot rock near the core slowly rises, while cooler rock from the crust sinks down into the core. And this creates giant circular currents. We call these convection currents. And just like ocean currents, they can carry heat from one place to another. But why don't all places on Earth's surface receive the same amount of heat carried by these currents? To understand that, let's dive deeper into how convection currents work. Remember, those currents are driven by the heat coming from Earth's core. And the heat escaping from the core isn't consistent across the planet. In fact, it varies significantly depending on where you are. This variation in heat flow from Earth's interior is called the heat flow anomaly, and it's due to the fact that the core doesn't emit heat evenly in all directions. Some spots receive more heat than others, and that's all thanks to the composition and thickness of Earth's crust. The crust varies in both composition and thickness. For example, the oceanic crust is made of dense, heavy rocks like basalt, and it's much thinner than the continental crust, which is made of lighter rocks like granite. The continental crust is also thicker beneath mountain ranges like the Himalayas, and thinner in places where the crust has been worn away, such as the middle of the Atlantic Ocean. As a result, heat from the core has an easier time escaping through thinner sections of the crust. For example, the heat flow anomaly beneath the thin oceanic crust in the middle of the Atlantic is more than twice as high as the anomaly beneath the thick continental crust in the middle of Asia. And when heat escapes more easily, the rocks near Earth's surface stay hotter for longer. Now, you might be wondering what happens to that heat as it makes its way up through the crust. And that's where things get interesting. When hot rock called magma pushes up toward the surface, it can pool beneath the crust in areas with a high heat flow anomaly. Eventually, that magma turns into solid rock, creating mountains. Places like Yellowstone sit atop these magma chambers. But not all rising magma makes it all the way to the surface. And that's where geothermal wonders like hot springs and geysers come into play. If magma comes close enough to the surface to melt part of the crust, it can form pools of hot water. And if the pressure is just right, that water can turn into steam, creating geysers. For example, at Yellowstone, rising magma heats groundwater, which turns into steam and erupts through the weak spots in the crust, creating those iconic geysers. So the higher the heat flow anomaly, the more likely you are to find geothermal features like hot springs and geysers. And it turns out that some places have more than twice the heat flow of Yellowstone. One of these places is the Afar Triangle in Ethiopia. The Afar Triangle sits on top of a triple junction where three tectonic plates meet. The Arabian Plate is moving away from the Somali Plate, while the Nubian Plate is moving toward the Somali Plate. The combination of these movements creates an area of low elevation that's perfect for magma to pool. This magma heats groundwater, creating hot springs and even geysers similar to Yellowstone. In fact, the Afar Triangle has the highest density of active geothermal systems in the world. That includes Yellowstone. Plus, the Afar Triangle has the hottest hot springs on the planet. The Danakil Depression, located within the Afar Triangle, is home to the Dalol geothermal field. Here, sulfur-rich waters reach temperatures of more than 200 degrees Celsius, hot enough to dissolve most rocks and create colorful pools of acidic water. Now, you might be wondering, why don't people use this incredible geothermal energy to power their homes or even their entire cities? Well, the Afar region does harness geothermal energy, but there are some challenges. First off, building anything in such a harsh environment is tough. Extreme temperatures, acidic waters, and frequent earthquakes make construction difficult. And to add to that, the Afar region sits on the edge of a desert. So even though they have access to a tremendous amount of geothermal energy, it's challenging to collect and use it in a sustainable way. Another place that could use a lot more geothermal energy is Iceland. Iceland sits atop the Mid-Atlantic Ridge, a massive mountain range that runs through the middle of the Atlantic Ocean. And like the Afar Triangle, it's also a triple junction where three tectonic plates meet. Two of the plates are pulling apart, allowing magma to rise and create new oceanic crust. And the third plate is sliding past the other two. These interactions create a lot of heat. In fact, Iceland receives about 60 times as much solar energy per square meter as the Sahara Desert. And Icelanders have been putting this geothermal energy to good use for centuries. They've been using hot springs for bathing and heating homes and greenhouses. And recently they've started using geothermal energy to power their entire cities. For example, the Olsen power plant in southern Iceland is the largest geothermal plant in the country. It harnesses steam from the earth to drive turbines and generate electricity. In total, it produces about 300 megawatts of power, enough to supply about 75% of Iceland's energy needs. Of course, harnessing this much geothermal energy isn't without its challenges. One of the biggest is finding suitable locations for plants like Olsen. Iceland's geothermal energy is mostly concentrated in the western part of the country, and building new plants can be expensive. But Iceland is committed to using more geothermal energy in the future. In fact, the government's goal is to produce 100% of the country's energy from renewable sources by 2040. It's not just Iceland and the Afar Triangle that are harnessing geothermal energy. Countries like New Zealand and the Philippines are tapping into this resource as well. In New Zealand, the government is working to develop the country's first geothermal energy storage system. By storing excess energy underground, New Zealand could use geothermal power to generate electricity even when there's not enough steam to power a plant. Meanwhile, in the Philippines, the government is looking to geothermal energy to replace coal. The country's first geothermal plant was built in 1961, and today it accounts for about 20% of the country's energy needs. As you can see, geothermal energy has the potential to power our homes and even our entire cities. But it's not a one-size-fits-all solution. Different regions have different geothermal resources and challenges. For example, places like Yellowstone and the Afar Triangle have plenty of heat but lack infrastructure and access to water. Meanwhile, places like Iceland and New Zealand have abundant water, but need to find ways to store and distribute geothermal energy. So as we look to the future of energy production, it's important to remember that no two places are the same. We can't just copy and paste solutions from one place to another. Instead, we need to take a localized approach that considers the unique geothermal resources of each region. But maybe someday we'll be able to harness geothermal energy as abundantly as other renewable resources like wind and solar. Thank you for watching this episode. I hope you learned something new and surprising. If you did, please hit the like button. And if you want to learn more about Earth's incredible geothermal energy, check out the additional resources. I'll see you next time.